Good evening and welcome to everybody. My name is Graham Wilcock. I'm the Vice Chair of the IMechE Germany Group, and it is my pleasure to welcome you today to this webinar entitled The Secret History of Fighter Aircraft Engine Development in World War II. The development of piston-aero engines were the dominant mechanism in determining fighter aircraft performance from 1939 to 1945. This lecture focuses on key technical and organisational differences between the German and British efforts, which had key impacts on both the airframe, aerodynamic design, and engine characteristics of both aircraft. The speaker presents a guided tour through the key difficulties experienced by German and British aviation engineers, using access to unique archival material, including the personal papers of Professor Willy Messerschmitt and Ernest Hives, Technical Director at Rolls-Royce. This webinar will last around 1 hour, as well as further time at the end for questions. If you wish to pose a question, you can do this by clicking on the Ask a Question tab, which should be just below the presentation screen. We will endeavour to address as many questions as possible in the time available, but if you wish to learn more about the subject, please go to www.calum-douglas.com. I would now like to introduce our presenter of this topic, Mr. Calum Douglas. Calum Douglas worked in Germany for Toyota Motorsport GmbH, applying Formula One engine technology to advanced technology demonstrator engines for Toyota Japan Road Cars Division. Returning from Germany, he worked for Jaguar Land Rover and Mercedes-AMG, and now runs an engine design consultancy. He began investigating piston engine development in wartime archival records and has spent the last 5 years researching and writing about it alongside working. He will publish 2 books this year, including a translation of the unpublished memoirs of Professor Dr. Engineer Calum, Chief Designer of Daimler-Benz Aero Engines. The second is a technical history of piston-aero engine development from 1928 to 1946, entitled The Secret Horsepower Race, and is available to pre-order from Morton's Publishing and Amazon. I would now like to hand over to Calum. Calum, to you.
Thanks very much, Graham. This is a bit of an odd experience for everyone, I think, because in all the lectures I've previously done, I can see everyone's faces, and at the moment I'm just staring at a screen, so it's quite a bizarre experience for me, and I expect for a lot of the people listening, but I think it'll still be quite good. And it's especially pleasing for me that Graham and Emma at the IMechE have organised this, because 3 of my lectures were cancelled just prior to this because of the COVID crisis. So it's nice to be able to do something despite of all the difficulties we've got at the moment. Just give me one moment. I'm just resolving one of the favourite technical difficulties that we all enjoy in these kinds of experiences. Just one moment. So the slide you're looking at the moment shows you a quote from Cyril Lovesey. And Cyril Lovesey was a Rolls-Royce engineer who was really the man most in charge of developing the Merlin engine throughout the Second World War. And one of the things Lovesey was quite frustrated about was that the reputation of British engineers at the time seemed to be really that they had sort of muddled through with a sort of combination of amateur guile and luck and help from America. And all these things have a degree of truth about them. But as you'll see in the presentation, I would really like to challenge some of the thoughts we have about the notion of who it was that was more organised and efficient in the Second World War with respect to aero engine development. And I think you might be surprised by some of the things that we find. So this was a quote from an article that Lovesey wrote for an aviation magazine just after the war. And he's sort of whimsically making a comment there that one would believe from the reports of all the fantastic achievements in Germany that what Rolls-Royce had been doing was some kind of amateur game, and this really wasn't the case at all. So something that frustrated me over the years is that a lot of the books I would read about the subject, which I've been interested in since a very early age, seem to be really quite poorly researched. And I think the reason for this is that engine development is not a particularly easy subject for a historian to tackle. And also, most of the information as relates to the German activities is naturally in German. So unless there were any technically trained German historians who knew about engine development, it was always going to be fantastically difficult to write a book about the subject properly. So I've really gone to quite a large amount of effort to try to really uncover what really happened, as opposed to just reading other books and collating them into a volume. So one of the first things I did after discovering that Carl Coleman had ended the Second World War as the chief designer of Daimler-Benz is that I found his son in Stuttgart and interviewed him a couple of years ago. And on my website, you can see a 1-hour video with his son, who's also, until he retired, an engine designer for Daimler-Benz in their automotive section. And his son, who's also called Carl, gave me all of his father's papers, which you can see resting on the glass table in that picture that was taken in his home in Germany. So that's really the first source that I had of information on Daimler-Benz activities. The other famous firm in Germany was Junkers Jomo, and they've been very, very difficult to research. But I did also travel to what was the east of Germany and found Ellie Harnitsch, who I'm pretty sure is probably the last living employee of Junkers Aero Engines, and she worked in the Aero Engine drawing office from 1942, and that's her work card there at Junkers. And she had a lot of fascinating stories. I think one of the most illuminating is that by the time the war ended, the entire drawing office was staffed by women because the men had all been sent to the front to Stalingrad, and from which they didn't come back. So that's quite astonishing. So the next source of information, which might surprise some of you, is that in an old aircraft hangar in Cambridge is stored about 3 or 4 million pages of documents that we, shall we say, borrowed from Germany in 1945. It's called the German Documents Collection, and it's actually still there. And all the boxes you can see on those shelves are German aeronautical papers which were taken from German firms by Britain, France and America in 1945. And most of the development records of Daimler-Benz, Focke-Wulf and so on are actually still kept there. So virtually all the material you'll see in this presentation is stored in these boxes in Cambridge. So I can really promise you it is it's a 0% Wikipedia presentation, which I think you'll be all pleased to hear. So I would like to really show why engine performance matters, and I hope this doesn't upset any airframe designers who are listening, but the simple fact is that once you've designed an aircraft, it's incredibly difficult to make it go any faster afterwards, because the only thing that's going to happen is that pilots are going to complain and ask for more things to be put in the plane, and it's only going to get heavier. So once you've built the thing, really the only way forward is to increase the engine power. So if we just have a look at the graph, you can see that the speed of the Spitfire, which is the white line, and the manifold pressure of the engine, which is the blue line, basically rise in tandem throughout the war, which really tells you in one very simple slide the development path that Rolls-Royce took during the war, which is basically to increase the supercharger boost. It's very, very easy to say that, and it's quite another thing to actually do it. And the Spitfire, you can see on the right, is I think the final mark that actually participated in combat, and it has a two-stage supercharger, and most aviation fanatics are well aware of the Spitfire Mark 9, which saved the RAF, and it's well known that this was really the moment when the RAF was saved. What's less well known is the story of why Germany didn't have their own version of that. And there are lots of stories about it, but most people don't actually realise that as early as 1936, Daimler-Benz actually had a two-stage supercharged fighter engine of their own. And really it's, I think, indicative of the colossally appalling management of German aero engine research in the Second World War, that they did as poorly as they did, because in fact they really had their own version of the two-stage Merlin half a decade before the war broke out. Another fact a lot of people won't know is that the men in charge of these engines were actually often very good friends, because like it is now, the engine development community is actually a very small group of people at the top. And George Bulman, who was the director of engine development at the Air Ministry in Britain, is on the left, and that's Helmut Sachse on the right, who did the same job at the RLM, that's the German Air Ministry. And Bulman wrote in his memoirs that the two men met in a brewery in Munich, and after quite a few beers, the quote I put at the top of the page is the line that he thinks was probably the final conversation between the two men before they never saw each other again, before war broke out. And this was in about 1938. And the two men were very good friends, and in fact, Sachse came to London to have dinner with Bulman in the 1930s. Fairly shortly afterwards, however, Bulman realised that things were taking a very, very serious turn for the worse, and both Bulman and other Rolls-Royce employees were actually invited to Germany to look round their engine development workshops to see what they were developing. And it's a very interesting story as to why this happened, but that's a topic for another presentation. That it's normally a cardinal sin to put text on PowerPoint slides, but I've chosen to do it here because I've made direct quotes from the original documents, and I think they have some innate power such that I think it's worth putting the words on the slides, even if it's breaking PowerPoint rules. That Bulman, as you can see, was right that he was very worried that because the Merlin was much smaller than the German engines, if they were developed at the same rate, they would soon be in an extremely perilous state of affairs. Jimmy Eller, another very important Rolls-Royce engineer, was also panicked. And really, after seeing the German developments, you can see what he wrote upon his return. And really, the story of this presentation is to understand why the warnings that these two men came back with didn't come to pass. And a large aspect of that is really the fact that Britain was actually the country that was efficiently run and ruthlessly well organised, and it was in fact Germany who were, for the most part, amateurish and appallingly badly organised. And this is just one example. So this is an organisational chart of the aero engine development group in Britain, and I won't go through all of it, but if you look towards the bottom, you see what's probably the most important part of it. And you'll see in the middle, about 3/4 of the way down, you'll see RTO, and that's Resident Technical Officer. So every single developer of parts and components for engines had an Air Ministry employee working on their premises for the entire duration of the war. And what this really meant was that men like Bulman had a direct line to what was happening in all of the different companies developing engines. And they weren't reliant on the company director telling them what the real position was, because as everybody knows, when you do that, everything's always fine. So what's very important to note is that Germany had no such system. And this is actually not just proven by omission, but in fact, the fact that Germany didn't have this system was one of the primary findings of the Royal Aircraft Establishment when they visited Germany in 1945. This is an incredibly important part of showing why Germany managed to go through the war with such poor organisation. And one reason is that their upper management didn't know what was really happening in the development firms. Now, most people know that aviation fuel in Germany was particularly problematic, and before the war, Germany had embarked on a massive program to build synthetic fuel plants. And what you're looking at here is the synthetic fuel plant at Pollitz, which is one of the key sites where aviation fuel was made from coal and hydrogen in Germany, because they didn't really have any crude oil reserves. During the late 30s, Germany had made a lot of conspicuous success promoting their development by breaking airspeed records. And this was seen as a particularly popular pursuit by the Nazi Party, who wanted to demonstrate to the world the innate superiority of German engineering. And Britain began preparing their own effort to try to break some of the world speed records that Germany had taken. And you can see on the bottom the Speed Spitfire, as it was called, which had a highly tuned Rolls-Royce engine to try to break the record. But the people in the Air Ministry correctly perceived that Germany was always working very hard on this. And I'll just read some of the letter. He says, I think it's clear we should not proceed with the Spitfire. I have suspected for some time that Germany was waiting for us to do so in order to do immediately a better one afterwards. And this was proven to be exactly the case. As almost immediately afterwards, the Germans broke the world airspeed record twice in quick succession with a Heinkel and Messerschmitt, which was called the Meshmit 109E, and this is actually a propaganda attempt to persuade people that the almost standard German fighter aircraft was capable of breaking the world airspeed record. And it also marked the start of a long tradition of lying about engine power. So, as you saw in the last slide, and can see now with this snippet I've pasted above the engine power graph, the record was claimed to have been made with a Daimler-Benz engine of 1000 PS. And in fact, this is a quite astonishing lie. It's not even vaguely close to the truth. So this is the real engine power graph from the actual record engine from the Daimler-Benz archives. And you can see at sea level it actually generated 2500 PS. So this was really an attempt to persuade people that the aerodynamics of the German fighter were so astonishing that it could break the world airspeed record with quite a low power, but it was actually a complete fabrication. Shortly afterwards, when the war started and the Battle of Britain began, German engines obviously began appearing in Britain in the form of crashes. And Britain, again, very well organised, immediately had a system whereby the crashed engines would be extracted from the ground by technicians and would be sent immediately to firms like Bristol and Rolls-Royce, where a complete metallurgical workup would be done on all the parts. The designs would be analysed by the engineers, and you can see that certainly the two gentlemen here seem to be very much enjoying a day out with a couple of spades. So these are two of the original tags that were used in the Battle of Britain, and all the fuel and oil was siphoned from all the German aircraft which crashed and into cans, and these cans were then sent to the laboratories of Shell and ICI, and they were then spectrographically analysed, and British technical intelligence could then work out not only the performance of the fuel but even which refinery it had come from based on looking at the exact composition. So British development work was actually highly scientific and organised, using state-of-the-art techniques in every respect. And really the concept of the British amateur in the Second World War needs to be, in my opinion, completely ditched as an idea. It bears no resemblance to the reality. The first German plane which was brought down in Britain was actually brought down about 2 hours drive from me in the hills of Lammermuir in Scotland, and within a few hours of the crash a transport had been organised and Rolls-Royce engineers were on hand. So that's William Gill, a Rolls-Royce employee, and they basically hacked through the engine mounts, and I think within about 12 hours of the crash the Junkers Yermo engine was in the development laboratory at Rolls-Royce, and they were testing the direct injection system. So again, the British technical intelligence system was ruthlessly well organised and efficient in every respect. Late on in the Battle of Britain, the Germans tried to improve the performance of their Meshmit, and this was done with the DB601N engine, which had a higher compression ratio and used their 100-octane fuel called C3. And this is a quote above it from the German Air Ministry records. And they actually fitted them first to the Meshmit 110, which was called the Destroyer, because it was having the hardest time against the British fighters. And it was left up to Goering to decide who would get the new engine. So you can see from the pistons, some of the British intelligence officers just put a chalk cross on the top to show you that the N engine had a flat top piston to put the compression ratio up. However, this was not a successful experiment, and in May 1940 it had been realised that actually this new German engine development had failed quite catastrophically, and essentially what was happening was that the Germans had changed the fuel composition somewhere between September 1939 and February 1940 for reasons of production, and they had originally designed the DB601N for a high performance fuel called C2, which had a slightly different composition. And the German engines are widely regarded as being incredibly sophisticated because they use direct fuel injection. However, it's not just a case of having direct injection and feeling pleased with yourself, because it brings with it all sorts of very, very complicated problems. So what I'm showing you here is what's called a distillation curves for the fuels, and it sounds a bit frightening, but it's actually incredibly simple. So each colour is just a different fuel type, and the vertical axis is just how much of it's evaporated. So it's not quite as simple, but if you just imagine filling up a frying pan with some of the fuel and heating it until it's all evaporated, essentially the temperature you need to heat the frying pan to achieve that is on the bottom axis. So what this basically means is that the German C2 fuel, which the engine had originally been designed to use, the blue, this evaporates completely at a very low temperature. It's almost completely evaporated at about 120 degrees centigrade. And the C3 fuel, which was brought in at the end of the Battle of Britain, is shown in the green curve. And you can see that it needs something like 40 degrees higher temperature to evaporate. And you might ask, so what? Well, the problem is that if you inject the fuel into the cylinder, the fuel is able to enter the oil because the spray can be directed and it actually impinges on the cylinder bore. And the quantity of the fuel actually goes into the oil and begins diluting the oil with fuel. And this always happens to an extent, but the idea is if the fuel has a reasonably low evaporation point, the fuel that dissolves into the oil will boil off again slowly as the engine runs and heats up. The C3 fuel had such a high temperature of evaporation that it did not boil up the oil again. And this basically destroyed the bearings of all the German fighter engines that used it, that had used the DB601N. And this was an absolute catastrophe for Germany, and it's really not a small problem, as I'll show you in the next slide. So that's what the bearings look like after they've been destroyed by the fuel diluting the oil. So after the dilution reaches a certain percentage, the oil stops working and the crankshaft begins chewing the bearings up. And so this is really what destroyed the first German attempt to combat Spitfire developments with their own engine development. The next attempt was Messerschmitt's Bf109F fighter, which was actually regarded as probably, in some ways, the best fighter that he designed in the Second World War. It was an extremely good fighter in many respects. But again, not long after it had been introduced, although they had made an attempt to sort out the fuel dilution problem, pilots again began reporting a series of catastrophic engine failures. And it took months to find out what the problem was, and they found that it wasn't a repeatable problem, which made it very, very difficult to diagnose. And what they actually found out was the Bf109F was the first Messerschmitt to use what's called a bag tank. So rather than an aluminium box, the tank is basically formed of several layers of rubber and canvas. And the idea of this is that it helps. It's basically a self-sealing fuel tank. So if it's pierced by bullets, it doesn't just drain out immediately. But in fact, the fuel reacted with the rubber that the tank was made of, and the particular reaction actually destroyed the anti-knock properties of the fuel. And the reason it took so long to diagnose the problem was that it took a few weeks for the reaction to take place. So if you put fresh fuel in a Messerschmitt 109F and took off, the engine didn't detonate. If you take an aircraft which had been sitting at the airfield for maybe a couple of weeks without being used, you would take off and the engine would experience detonation, and shortly afterwards the pistons would be ruined, and this could be serious enough to cause the pilot to have to bail out. So really this is an example of incredibly poor planning, because this could all have been discovered in testing, and so they really hadn't planned their engine or fuel development programs at all well. But nobody knows that these are the kinds of problems that were happening for the Germans. That's exactly what happened. Slightly afterwards, in 1942, things did take a turn for the worse, however, for the RAF, when a bomber flying over France in Abbeville took a photograph and found a completely new German fighter aircraft. And so this is the first photographic evidence that the British found of the existence of the Focke-Wulf 190 fighter aircraft. And the Focke-Wulf 190 was the creation of Kurt Tank and Professor Tank, who you can see in the top left image there, in the Focke-Wulf 190 was famous for flight testing all of his own aircraft. And the Focke-Wulf 190 was far superior to the Spitfire of the time, which was the Mark V, and it really was a very, very, very serious situation for Britain. And letters about the Focke-Wulf 190 were even sent to Churchill from the Chief of Air Staff, Sir Charles Portal. So it was really a problem on a national level. And some of the intelligent things that the Germans had done here with the radial engine is that it's the first engine to really have a complete system of quick disconnects. So the engine can really be moved in as a separate lump and just quickly connected to the fuselage. So if you look in the top right photo, you can see all the quick connects and so on. And it also had what you can see in the bottom right photograph, which the Germans called the Kommandogerät, which basically is a command module, and it's essentially the world's first mechanical engine control computer. And it controlled all the aspects of engine performance, which meant that the pilot didn't have to do anything at all, whereas in something like a Spitfire, you certainly had to choose which supercharger gear you were in, and at certain points you could choose if you were running a rich or a lean mixture. And the American aircraft were even less well managed and had all sorts of terrible problems because the pilots had to look at so many different things at once. So for this reason, it was a really formidable fighter aircraft. However, just when Germany thought they were on the front foot for a change, Edgar Peterson, who was running the German testing station called Rechlin, came back with reports even before 1942 with problems with the BMW 801 engine. And this is a direct quote from his discussion at the German Air Ministry meeting in Berlin. And as you can see, he's saying that the combat forces have no confidence in the operational safety of the BMW 801 engine. And he's suggesting that to make it reliable, they're mostly having to be flown at only half power. And so really, it's quite astonishing because although the Focke-Wulf 190 caused such a problem for the RAF, actually in its first year, it was actually completely crippled by a series of engine catastrophes. And I've chosen a photograph here which has got a later date on it, it's actually the same problem, it's just a nicer photograph, which is why I've used it. So I'd like to explain what actually happened. And what actually happened was that the valves and the spark plugs had basically caused the engine to detonate. And this was basically all caused by material shortages. And this was a situation which the British engineers did not have to deal with. And in fact, in post-war interviews, Rolls-Royce engineer Geoffrey Wild was asked if he had ever experienced any shortages, and he said, no, not at all, we're never short of anything. And what you'll see here has no equivalent in the Rolls-Royce archives because such a thing never happened in Britain. And the chart you'll see at the bottom there is the materials savings chart for the Daimler-Benz 601 engine. So it basically shows the reduction in the use of key metallic elements in the engine between April 1940 and April 1942. So we can see nickel, copper, tin, tungsten, molybdenum and chromium. So between 1940 April and 1942, the DB601 had the amount of nickel reduced by about 2/3. And what's even more shocking is that this had been done with incredibly poor coordination. So Helmut Sachse, who I showed you at the beginning talking with George Bulman, had actually been sacked in 1938 because he didn't get on with the Nazi party. And he had been replaced with Wolfram Eisenlohr, who's in the image to the bottom left of the slide. And on the top is Erhard Milsh, who is basically the Secretary of State for Air. And what I'm going to show you above that is actually a slide from what's called the stenographic record. So because the Nazis were paranoid about being accused of doing something they hadn't asked to be done, most of the meetings were also recorded by a court stenographer. So these are the actual spoken words of each man. They're not paraphrased or meeting minutes. And so after the catastrophes with the BMW 801, Milsh says, "How much nickel are we using now?" And Eisenlohr says, "Oh, we used to use 15% nickel, but today we have to use 8. And this is the amount of nickel they were putting into the exhaust valves. And this single calamity had been solely responsible for all the reliability problems that were most significant for the Focke-Wulf 190. And most shocking of all is not that they had the problem with the shortages, but how long it took to find out what had happened. And actually, this problem with the low nickel valves is what reduced the power output of every German fighter engine on the Western Front for over a year. And eventually, it was realized that nobody had told the technicians in the test engine cells to use the new low nickel valves in their test engines. So, for example, this is a test engine at the IG Farben fuel laboratory, and it's a single cylinder from a DB601, and they had fully instrumented engines to test the performance of fuels, and because they didn't have a fully instrumented engine in the aircraft, they had to do all this testing on the ground, and nobody had replaced the original high nickel valves with the low nickel valves. And what this meant was that it took a year to find out what happened, because all the testing done in the test cells showed no problem. And it's really, I think, an organizational catastrophe of almost unbelievable proportions. And it's inconceivable that something like that would have been permitted to happen in Britain. So shortly afterwards, Milsh tries to work out what they can do with these low nickel valves, which limit the boost of their fighter engines. So he asks Peterson, "What can we do? Can we just reduce the engine power?" And they had been experimenting with thick pistons, and so to this day it's a story that the German pistons were weak, and so they made thicker ones which fixed it. In fact, they tried the thick pistons when they didn't know what was happening, and they just took longer to be eaten through. They didn't solve the problem. And Peterson says, as you can see, that it only took 1.5 hours for the piston to be completely eroded with detonation. So it was an absolute catastrophe, and it completely destroyed the operational effectiveness of the Luftwaffe for well over a year. And just to show you what that actually looks like, that's not a piston with detonation damage. That is a DB601 piston with detonation damage. So you can see this is a complete engine failure. This is an absolute disaster. The other serious problem here is that they didn't have the nickel for their future engines. So the next engine they were trying to make was the Daimler-Benz 605, which was used in the Messerschmitt 109G, which was the main opponent for the Spitfire from about 1943 onwards from the Messerschmitt firm. And Eisenlohr explains to Milsh that we can't replace the old valve alloy, so actually the solution is that they have to chrome plate all the low nickel valves to try to get them to stop being attacked by the corrosive environment in the combustion chamber. And BMW had actually developed that first for the BMW 801, and no one had told Daimler-Benz. So in fact, BMW had worked out that valve chroming stopped the detonation, and months passed before Daimler-Benz were informed. This was chiefly because the Daimler-Benz engine was water-cooled, and the situation had to get a bit worse before they began experiencing the failures. But it's unbelievable that knowing the metallurgical restrictions, they didn't move all the valve production immediately to chromed valves. And that's why today, if you see people selling Daimler-Benz valves on eBay, they always look very shiny. It's because they've been chrome plated. So this is the DB605 engine that's been captured, and this is being under study at the Royal Aeronautical Establishment, and this had the chrome plated valves from about the middle of late 1942 onwards. So even with the chrome plating, it wasn't a completely sufficient solution, however. So much like the communiques about the Focke-Wulf 190 had gone all the way up to Churchill, discussions about engine problems had gone all the way up to Hitler. And Milsh had said to Goering on May 1942, if we don't produce this engine, the whole fighter program is basically over. And Goering came back and reported that the Führer had said, we can't push the aircraft engine quality any higher in terms of the economy because it's critical for the safety of the engine. However, Hitler, I don't think, was a metallurgist and hadn't realized that the safe limit for how much they could cut back the nickel in the valves had been reached and then passed through a very, very long time ago. And they were way past the level of being able to just stop the progress. In terms of things that actually happened in the war, which had a real effect on these sorts of problems, the 8th of November was Operation Torch, which is the Allied landings at Algiers, and this is French Morocco. And not very many people know that actually French Morocco was more or less the only source that Germany had for cobalt. And one of the solutions German engineers had tried to make for their valves was to apply a stellite coating, which is a high cobalt alloy, to the valve head to stop it corroding. And you'll see the photograph here, which is at the ends of two Daimler-Benz 603 valves after 70 hours running. And the left one has been chrome plated, and the right one has been coated with a hard coating of stellite. But because the Germans had cobalt restricted because of the invasion of French Morocco, they had to develop a low cobalt stellite, which was much less corrosion resistant. And you can see that both the solutions to the poor valve materials didn't work. And this scaling that you can see on the valve, which looks a bit like rust, these little sharp edges glowed white hot in the combustion chamber because they're very small, sharp edges, and this is what caused the detonation. So even with the solution to the low nickel problem, this scaling of the valves was the primary factor which limited the supercharger boost that the Germans were able to apply in the Second World War. And in fact, it was not limited by the fuel quality, which is a fact that's not very well understood. It wasn't just the sort of raw engineering of the engine which was in trouble, though, because in fact the British had also been much better than the Germans had with the design of the cooling systems. And in November 1942, Professor Messerschmitt at the German Air Ministry meeting in Berlin was getting very, very angry because he was being heavily criticized for the performance of the Messerschmitt fighter aircraft. And he retorted, well, what do you expect? The radiators on my aircraft have to be twice as big as those the English use. Milsh says, well, how have we not noticed? You're addressing Eisenlohr. And Eisenlohr says, well, you need very high pressures to do this, and we get leaks in the engine castings. And Milsh gets very fed up and basically threatens Daimler-Benz with having their complete engine design department dissolved and having their engineers all sent to UMO and to have them build UMO engines. And these are the spoken words of each man. So this is, again, the stenographic record. So Milsh then realizes, well, if we can do this, we can get rid of 2/3 of the radiator drag. He says, well, maybe this will be 80 kilometers an hour for our fighter. And Eisenlohr, who was supposed to be organising these developments, says, well, it's only 45, but in fact, 45 kilometers an hour is more than enough difference to make the difference between a reasonably even-sided engagement and the other fighter being basically completely obsolete. So what had actually happened is that the Germans had failed to develop high pressure, high temperature water cooling. And essentially, if you can allow the water in the engine to run at a very high temperature, it conducts much more of its heat to the outside air, and it also absorbs less heat from the engine itself. But to do this, to stop the coolant boiling, you need to apply a very high pressure to it, which puts all sorts of very intense mechanical constraints on the engine, which takes several years of intensive development to organize. Nallinger was basically the managing director of Daimler-Benz Aero Engines, and in the same conference he was trying to defend himself from the criticisms from Professor Messerschmitt. And again, this is the spoken words from the stenographic record. And Nallinger says, well, the Merlin's only 27 litres, but it's a bit heavier than ours, and, well, the Merlin 61, okay, it's better, but it's the first one that's beaten us. So this was his attempt at defending the performance of Daimler-Benz against the Merlin 61 development. And this is actually quite a famous aircraft now. It's very well known, and a lot of people have speculated why Germany used a captured Spitfire to put a Daimler-Benz engine in. And actually, most of the reason they did it was to test the cooling system. So that was the primary purpose of this test. It wasn't really to see if it was a good aircraft or not, although they did look at that as well. And they noted that putting a Daimler-Benz engine in the Spitfire, using the original radiator, which was half the size of the Meshmit 109G, it only had 4% less cooling efficiency. So it's a really staggering difference, and that makes a huge difference to the drag of the aircraft and consequently the speed of the fighter. And you may find this a bit confusing if you've been to a museum recently, because if you look at the size of a Messerschmitt radiator, that's the bottom image, and compare it to a Spitfire radiator, the top one, it's the Spitfire radiator which appears to be the hulking piece of apparatus, and it's the Messerschmitt radiator which seems to be the sleek, well-installed item. But it's a bit more complicated than this. In fact, the radiators are about the same size, but the Meshmit 109G has two of them. So the Spitfire Mark 9 achieves all of its engine cooling with one radiator, and the Meshmit 109G has two, so it's actually double the radiator area. The Spitfire also has a radiator on the opposite wing, but that's used for the water charge cooler and the oil cooler, and the Meshmit 109G also has a separate oil cooler. So in fact, a huge amount of drag was lost in this, and it was really due to poor engine development. And in fact, the concept of high pressure cooling was developed by the Royal Aeronautical Establishment as early as 1932, and had been pressed forward by organised men like Bulman and Hives at Rolls-Royce. And just to show you the kind of development work it needs to do this, that's a drawing of a Spitfire radiator, and it really is built like a tank. It's covered in reinforcement ribs, and the cooling tubes, which you can see on the right, have all this internal reinforcement. And that's because the Spitfire had to have a water pressure of up to 4 atmospheres to stop the coolant boiling at high temperatures. Conversely, if we look at a Meshmit 109G radiator tube, which is this photograph on the left, it's actually made of a round tube which has been squashed, and there's 2 little pips in the middle which stop the tube being completely squashed so the coolant can still pass through it. The trouble with making the tubes like this is that if you pressurize them, it does what you see on the image on the right. So the tubes literally just inflate like a bicycle tire. So this is one reason why the Germans couldn't use high pressure, high temperature water cooling in the engine, because none of their cooling system components had been developed to use it. It's not as simple as just pressurizing it. And Messerschmitt again came back at the conference in Berlin at the Air Ministry on the 2nd of December 1942. And again, this is a spoken word stenographic record. May I say something about these engines? How have the English managed to get 1600 horsepower out of a 27-litre engine? I believe we are not on the right path with engine development. The superiority of the Merlin 61 is clear. I wonder why it is not possible they can get out of the 601 the performance the English have. So really, Professor Messerschmitt has got a lot of flack for the fact that his fighter performance late in the war was not a match for the Spitfire, but he really did understand why it was, and he's one of the few people who spoke clearly and logically about it in the Air Ministry meetings. So Junkers Yomo had decided to do something about this, and they had designed the Yomo 213 engine, the final version of which you're looking at, which was captured and taken to the Wright Field facility in Ohio in America. And it did have some very neat gadgets. And if you look at the supercharger, which is quite visible on the left, you can see it has a sort of set of vanes around the inlet. And what these vanes are, it is what we would call now a swirl throttle or an IGV, and it's a variable set of guide vanes into the supercharger. And this essentially means that the power of the engine at low altitude is considerably increased, and these variable vanes are used instead of what the Spitfire would use, which was something like a butterfly throttle. So this is basically a method of reducing the pumping losses of the supercharger, and you'll find that something almost identical to that is to be found on all of the current Formula One engines on the grid. The only difference is the number of blades and the exact shape they use. The next advancement that Junkers had was an oil centrifuge. So they had realized earlier on that if you have air bubbles in the oil, it just allows the crankshaft bearings to be destroyed because the oil becomes compressible the more air is inside it. So if you look in the middle of the photograph, you can see there's a little tumbler there, and that basically spins at high speed, and the thick oil goes to the periphery, and the air bubbles, which are less dense, are taken out the middle. And this was a key reason why the Junkers engines had far less oil system problems than the Daimler-Benz. Conversely, in this respect, the first Merlin engines were quite primitive and put the oil into the crankshaft bearings from the outside. And essentially what this means is that the oil has to fight the centrifugal action of the crankshaft spinning to get into the middle of the crankshaft, because it's spinning at several thousand RPM. So the oil can't get into the crank unless it fights against the centrifugal action of it being spun outwards. So that's really what Junkers had been trying to design into their latest engine. So this is just a couple of pages from some Junkers documents to show you with a bit more clarity what's happening. So the green arrows to show you how the oil's fed into the middle of the crankshaft and not in through the edges of the bearings. And not only that, but in the end of the crankshaft, if you look at the top right-hand picture, there's a tiny little air oil separator which just goes into the nose of the crankshaft. And when I showed this to some colleagues in a previous engine design office I'd worked in, they were absolutely stunned, because this little widget is almost identical to that which was being used on a current top-level racing engine. That's just a sort of blown up view, so you can see that a bit more clearly. So this goes into the end of the crankshaft. The air bubbles come out where the red arrows are, and the oil free of air comes out where the green arrows are. So this was a huge technical development. So an example of, really, I think, a very good example of how the whole German system was organized here. So this is a slide from German intelligence, and it's showing the projected developments of the Spitfire. So it's showing you at the top Spitfire Mark 1, then to Mark 2, and from 1943 onwards, these are projected developments. This is what they thought we would come up with next. And it's about an 80-page report, and you can see how much time has been spent producing these colourful diagrams and elaborate charts. And I don't know how long it would have taken to prepare this document, but I would think several weeks would have been needed to complete it, and it looks very beautiful. And if we next have a look at what a British intelligence document on German aircraft developments looks like, you can see it here. And it's just a simple page of typed text with some hand-drawn arrows on, not even drawn particularly well, just to show what they thought the projected developments might be. And this probably took about 15 minutes to draw. It doesn't look very nice, but the fact is that this could be sent out to British firms within about half an hour, and the German document would have probably taken weeks, by which time the information was useless. This really tells you, in a nutshell, what the entire German system was like, is that a lot of it was done for show and not for effect. And although the British stuff might not look so shiny, it was at least effective. Other huge problems were happening in Germany. In fact, Hitler had allowed hundreds of engine development engineers to be conscripted and sent to the front. And in fact, the engine test cells at Daimler-Benz actually stopped at various points in the war because the test cell engineers had been conscripted and sent to the front. So you can see at the bottom there, Milsh is saying, well, this is unbelievable. We've got 4,000 engines, 2,000 engines are waiting to be tested, and the engineers have been conscripted. So it's almost unbelievable. And by comparison, if we look at what happened in England when there was talk of taking engineers away from Rolls-Royce, this is a letter from Ernest Hives, the technical director of Rolls-Royce, to Bulman at the Air Ministry. If you just look at the top bit first, replying to your letter of August the 30th, of all the colossal impertinence I'd ever heard is your suggestion that Ford should receive skilled labour from Rolls-Royce. You can take all the men you like away from Derby, but you take responsibility. Fords are a far bigger organisation than Rolls-Royce. Why the hell don't they look after themselves? Shortly afterwards, another memo was sent back saying Major Bulman to arrange that skilled people at Glasgow, which was a Rolls-Royce factory, are not called up for military service. And you might think, well, this is just an obvious comparison of a Nazi state compared to the British, and that's true, but in fact, Americans did it as well. So when Hives visited America in 1942, he came back and in fact wrote a scathing report on the standard of engine development at Wright Field, which was the equivalent of the Royal Aeronautical Establishment. In fact, this is a direct quote from Hives. He just said there was a lamentable lack of understanding and clear thinking. And they don't have the people in numbers or qualities to anything like carry out the work. And this was because the Americans had allowed huge numbers of their engineers to be conscripted into the military. And Bulman wrote the same thing and realized that, in fact, the American engine development program had also suffered from conscription. So it's not at all something you can take for granted that an organized democracy wouldn't allow something like that to happen, because it did in America. And it didn't happen in Britain primarily because of men like Ernest Hives. In Germany, meanwhile, probably their most famous engine development scientist, Dr. List, who had so many honorary degrees that they gave up putting doctor in front of his name and just said HC Malt, which just means there are so many doctorates that it's not practical to fit them on the page. And in fact, Dr. List spent large parts of the war writing reports on how to improve the Merlin engine. And this is a translation of one of the reports. And he had spent something like 6 months on this report trying to work out how to improve a Packard Merlin. And this was done to project future development paths that the Allies might like to use. And I think you'll agree it's an absolutely criminal misuse of who's probably the greatest engine development scientist in Germany and the equivalent of Harry Ricardo. And he wasted half the war on reports like that instead of developing Germany's own engines. Going back to a slide I showed you right at the start, we talked a bit about the German synthetic fuel program, which is quite famous, and they rightly get a lot of credit for it. But near the end of the war in Britain, we were developing 150 grade fuel for the Spitfire, which is actually mostly used for chasing V1 flying bombs early on. And in fact, all the development work which had been done to develop 150 grade had been done by Ronald Holroyd, the research manager at the ICI Billingham plant, where Britain had in fact been running their own synthetic fuel program since 1936, and the Air Ministry had worked with them to start developing synthetic aviation fuels even 2 years before the outbreak of war. And it's completely unknown, I think, to most people that Britain developed their own synthetic fuel program, which were in many ways just as advanced as the German synthetic fuel programs, but for some reason they've remained almost unknown in popular history. So just going through a brief overview of the calamities that befell German fighter aircraft, the Messerschmitt 109E and F were ruined with the DB601 engine because of oil dilution, because the fuel hadn't been properly developed. The 109F had been ruined with the 601 engine because the rubber fuel tank had reacted with the fuel, destroying its anti-detonation properties. And the Messerschmitt 109G and Volvo 190 had both spent over a year being completely handicapped because the valve materials had completely destroyed their ability to make their peak supercharger boost. So just to sort of make a few brief points about how Britain won really, there are hundreds of points you could list, but I would say in engine development, the Resident Technical Officer program was an incredibly important organizational difference. As you saw, men like Hives refused to allow their key engineers to be conscripted, whereas in America and Germany, their engine development programs were severely retarded by the conscription of their engine design and test engineers into the military. Our 150 grade fuel all came from initially being developed from our own indigenous synthetic fuel program, which made fuel from coal and hydrogen and not crude oil. Rolls-Royce cancelled or mothballed really all of their outlandish engines really in the first year of the war and concentrated on the Merlin, which was actually really a very, very basic engine in most respects. And finally, Britain didn't get rid of their most qualified technical leaders because they didn't agree with the political situation. Now, it's very easy to think that, of course, the German engineers blamed the management because that's what anyone would do in that situation, would be to blame their boss in 1945 when their job was to develop high-performance engines. But in fact, William Scott Farren, who was the director of the Royal Aeronautical Establishment, visited Germany in 1945 and wrote what's called the Farren Report, which is very comprehensive. And Farron was not a stupid man. He had a degree in mathematics from Cambridge, and in 1953 was made a fellow of the American Institute of Aerospace Sciences. So he was a preeminent expert in aeronautics. And in his report, you can see he wrote that really the lack of direction in higher planning is the most obvious explanation for what went wrong in Germany. And they tried to find out if that really was the case. And you can see that he wrote, "We heard and saw nothing to make it believe that in the case of German effort to conceive, develop and manufacture aircraft as weapons of war, the blame for failure can be placed elsewhere." So it's really indisputable that poor management was in fact the reason for the problems that the German fighter aircraft industry faced. And it was in fact the British who were by far the better organised and better led. And probably the ultimate tribute to the fact that you've conducted a successful program is the fact that this is the aircraft that broke the world airspeed record for piston engines a few years ago and reached 554 miles an hour at sea level. And it does look awfully like a P-51 Mustang with a Merlin 61 engine, and that's because it is. So I'd like to conclude by saying that if you are able to break the world airspeed record 75 years after you first designed something and no one else can afford to beat it, I think you've done quite a good job. So that brings me to the end of the presentation, which I hope you've enjoyed even in this slightly different online format. And I'll now be happy to accept any questions that you've been able to type in during the presentation. So thank you very much for taking the time to listen to me. You're all busy people, so I really appreciate it. So thank you very much for coming, and thank you very much to the IMechE for organising this.
So that's me back again now. So I think I'll return that thank you to you, Calum, for presenting that very, very interesting webinar there. We do have a few questions, and I'll start off with the first one, Calum. If I can just check that you can hear me properly.
Yep.
So the first question is, and I'll just read it straight off. So considering the other design aspects of the Focke-Wulf 190 and TA152, notably weight, what was the high point of the BMW 801 engine design that imbued Kurt Tank's designs with their outstanding performance?
Well, I think as you've seen that in the early years, the aircraft was actually handicapped by a whole series of engine disasters which really restricted the output of the BMW engine. So I don't think you can really say that the performance of the aircraft is due to any exceptional power output from the engine. It was just a very large engine. In terms of its effectiveness as an aircraft, I think you can really say that the Commando Gerät, or the mechanical computer, is probably the single most important part of what made it an effective fighter, because it just removes load from the pilot. And I think although there are many factors, I think you can say it's the development of that piece of apparatus, which, if I had to pick one thing, is what sets it apart from other engines. Actually, the Bramo company actually designed the computer, and BMW bought Bramo and developed it. So credit should actually go to Bramo and not BMW for the mechanical engine computer control.
Okay, thanks very much. Did you find a link in your research between Mercedes-Benz aero development and the famous Silver Arrows racing cars of the late 1930s? They had two-stage supercharging, which was very lightweight.
It's a very, very interesting question. And in fact, the RLM, the German Air Ministry, contracted Porsche to make a study on applying Grand Prix engine technology to aero engines during the war. And Porsche laid out two different engine layouts based on their experience with Grand Prix engines at the time, to see if they could make a smaller, lighter, more powerful engine than was being proposed by the aero engine firms. And essentially, big problems with it were that the Grand Prix engines of the time were mostly using either methanol or a very methanol-rich fuel to achieve the high performance. And the trouble with methanol is it has an extremely low calorific value, which means you have to carry an awful lot of it to go anywhere, which in an aircraft is a really serious problem. So once you factored in the fact that you can't use the methanol-rich fuel and all the other constraints which suddenly apply to an aircraft and don't apply to a Grand Prix car, when Porsche sent the report back to the Air Ministry, they basically concluded, by the time we've taken Porsche's best attempt at an aero engine and applied all the constraints that apply to it that don't apply to a Grand Prix car, its performance is actually not dramatically different to the aero engines that we've already got in production. So I think it was very, very difficult once you actually get into the details to really apply a Grand Prix engine technology directly to the aero engines, because there are so many constraints which are so specific to it. In terms of the superchargers, I showed you at the beginning that Daimler-Benz actually had a two-stage supercharger in 1936, and in interrogation records of German engineers in 1945, one of their key complaints was that once the Germans had got their early engines in production, the German Air Ministry basically more or less fixed the specifications and put so much red tape on making big changes that more or less the aero engine firms, for a period of about 3 years, basically gave up on any radically new developments, because they knew that there was absolutely no appetite at the German Air Ministry for them to come in and say, I've got this new engine, but it's going to take 8 months of development to get it done. And so there was about a 3-year development hiatus between something like 1938 and 1941 before they realised they were in trouble. So I think these two factors put together explain why some of the astonishing achievements of German Grand Prix engines perhaps didn't visibly make it into the aero engine designs.
Great, thanks very much. Stanley Hooker, in Not Much of an Engineer, asserted that the Merlin, with the carbureted fuel going into the eye of the supercharger impeller and being evaporated, effectively cooled the charge, giving the engine a power advantage. Would you care to comment on that, please?
That's certainly absolutely true, but there are numerous complications with it. So what Hooker writes there is absolutely the case. However, it doesn't come for free. So if you inject the fuel with a carburetor or a fuel injector at a single point in a very long engine like a V12, the distribution of the fuel between the cylinders becomes quite poor. And what this means in an engine which is running at the detonation limit is that you have to put in the amount of fuel necessary such that the weakest running cylinder doesn't detonate. And what this means is that the rest of the cylinders will all be a bit richer than they really could have been. And what this means is that if you put the fuel in at a single point, the fuel economy will suffer quite noticeably. The other thing that can happen is that if you fill the entire inlet tract with fuel, you can get backfires, and they're actually really quite catastrophic things which can actually literally blow the back half of the engine off. The whole supercharger can be thrown off the back of the engine because all the fuel in the exhaust inlet pipes ignites maybe from a hot valve or something like that. And so you actually basically need to fit anti-flashback screens, which is a sort of dense wire mesh in the inlet system to try to stop the backfire flashbacks from propagating back down to the supercharger. And additionally, Rolls-Royce had to make the supercharger casing incredibly robust, basically to say, well, we're going to get some backfires. When they happen, we can't allow them to actually blow the engine up. So if you look at the Rolls-Royce supercharger, you can see it's an incredibly dense pattern of bolts holding it all together. And it wasn't just to make the thing sturdy, it's because it had to keep together when you have backfires. So it's a system which does work, but it's not without problems. Germans, to an extent, had their cake and ate it because they used methanol water injection before the supercharger, which had the same cooling effect through the compressor, but didn't really influence the main fuel flow into the engine. So I think it's not as simple as just saying that was the best idea. I think it depends what technology you've got, and probably that was the right solution at the time, because as was shown by Germans, petroleum direct fuel injection is actually incredibly complicated, and it's still very difficult to get right today. And I think probably it was the correct solution to have the slightly more primitive solution that Rolls-Royce used, because it really took Germany until halfway through the war to get their direct injection system working. So there's a bit of a yes and no answer for you on that one.
Okay, great. We have several more questions, but I think we're starting to run tight for time. So I think I will earnestly thank you again for your time tonight. I will thank the IMechE for hosting this event, and perhaps if we can just finish up with a fairly simple question, perhaps your opinion. So I'm going to pose this question, and I'm sort of looking for two answers really. First, from a engineer's viewpoint, and then secondly, perhaps from a more schoolboy viewpoint. And the question is, in your opinion, Calum, what was the best fighter in service during the Second World War?
So I think the thing which has surprised me in the research for doing my book, which is really the reason it's taken so long, is because it's strictly archival. So everything in the book is because I've read it in an archive document, and so I've read a lot of documents. And what I've really been surprised about is that the de Havilland Mosquito, it's had a good reputation, but I hadn't realised that really in the case of the Mosquito, I actually think that its legendary status is actually undercooks how well it was regarded in the war. And I think the Spitfire has gone a bit the opposite way. The Spitfire is regarded as a legend now, but actually it pains me to say it, but if you read through the German Air Ministry meetings, there are not many comments saying, oh no, the new Spitfire's here, whereas they are filled with enraged conversations with Goering about the Mosquito. And so I really think that from an engineer's point of view, I think the Mosquito was the best fighter. Although it's a twin engine aircraft, it still was employed as a fighter. And I think to use the reason I say that is that it used really a brand new construction technique in terms of the technology of the time, which is a sort of wooden composite. It's really the first composite aircraft. Although it's made of wood, it's not made of wood in the same way a piano is made of wood. It's a very, very complex system of mouldings and pressings, and wood applied in different layers and different kinds of wood and bonded, and it's really a composite aircraft. And I think the aerodynamics were also astonishingly good, and they actually fitted the Mosquito with really mostly obsolete Merlin engines throughout the war. because the aerodynamics was so astonishingly good. It was actually able to do its job without the latest Merlins, whereas the Spitfire had to be always fitted with the very, very latest Merlin to be competitive. So really, I think the Mosquito, for me, is astonishing, because it's clear that the Germans really hated it beyond measure, more than any other aircraft, really. I think from the sort of schoolboy appeal, however, I have to say the Spitfire, just because of the looks. And yeah, that's what I'll say about that.
Okay, Calum. Well, thanks again for that. I've just seen a whole load more questions come in just at the end there. These questions will be sent on to Calum, and perhaps Calum can either come back to them in due course, or come back via LinkedIn, or perhaps a second webinar. Who knows? To that end, I will wish you all a very good night and the very best regards in these times. Calum, thank you again, and to everybody, thank you very much for your time. Good night.